Lesson 314. We're going to look at polar functions, and specifically, when we look at polar functions, we're going to look at their graphs. Now, something that's really interesting about polar graphs is number one here. This says it's a polar function. What's it mean to be a polar function? A review from Unit 1. What's it mean to be a function? That it can pass something. What can it pass? It'll pass the vertical line test. What we're going to see are these graphs might not pass. Actually, I'd go further and say they just basically won't. Graphs might not pass the vertical line test, but they're still polar functions. And I'm going to show you why when I get to example 2. But I want to put that in front of you right now that we're going to be looking at polar functions, but it might not pass the vertical line test. We'll talk about why is it still considered a function if it doesn't pass the vertical line test. So that's the first thing I want to start you off with here to get you kind of thinking about this as we go forward. So there's a way that traditionally is taught how to graph polar functions, and it is in the form of example 1. I do not like this method, but because it is traditional, and tradition is worth something, I'm going to walk you through how we can. So what we're going to do is we're going to look at this polar equation right here, and we're going to try to graph it on a polar coordinate system here. So let's begin. If I were to plug in a 0 in for sine, and it might help us if we looked at a unit circle to get the values. Sine, we're talking about sine here. So on the unit circle, if I start at a 0, I guess I could just go over here. What is the sine value? Remember, sine is which variable? Y. What is the y value when we have a sine of 0? What's that y value? 0. So what we have here, if I plug this in, I would have 4 times the square root of 0 over 2. That can reduce to become what? What is 4 times 0? Square root of 0 is 0. What's 4 times 0 divided by 2? 0. So here's how you'd graph that. We learned last class. You'd go to 0 radians, and you'd plot it on the circle that is a radius of 0, which means you plot it at what we'd call in polar the pole. We plot that at the pole. Now let's go to our next point. The next one, if you remember sine function, it's periodic, and it's like a wave. It's got a pattern. As I go up to pi over 6, you can use your hand trick here. Which finger is our pi over 6 finger? Ring. If I bent my ring and flip my hand over, the y has increased from where it was a square root of 0. Now it's a square root of 1 over 2. Okay, that can also reduce. What is 4 times the square root of 1 over 2? That is the value of 2. So at pi over 6, I want you to go out to the second circle and place a dot. That's the second point. Now, hopefully you remember that sine and cosine, they follow a pattern. What's gonna change here is my square root. My square root's gonna keep increasing until it gets to 4. So I'm gonna go ahead and just fill these in. Let's be quicker. So I'm just gonna fill these in. What am I changing? Each time my square root is increasing until it reaches 4. So what happens to the sine value after you get to 4, which is right here on the unit circle? It starts decreasing, and it's going to decrease all the way down to -4. Let's go ahead and fill those in. 4 times square root 3 over 2 on the second line as we begin. 4 times square root 2 over 2. 4 times square root 1 over 2. 4 times square root 0 over 2. If you don't know why I don't like this method, it's because it's tedious. See how tedious this is getting? I've counted down to 0. I need to count down to the negative square root of 4. So I'm going to continue counting down. So my last box on the second table here is 4 times negative square root 1 over 2. And at 3 pi over 2 is when sine reaches its minimum. That's when it's negative square root 4 over 2, which is the same thing as -1. And then I start counting back up again. 4 times the negative square root of 3 over 2. 4 times the negative 2 square root of 2. 4 times negative square root 1 over 2. Now, question for you. Does everybody see sine's pattern? I need to make sure you see the pattern. What was the pattern of all these numbers I wrote in black? The square root increased until it reached what number? 4. And then after it hits 4, it decreases all the way till what number? -4. And then once you hit -4, what happens? It starts increasing again. Okay, now let's reduce these and plot them. This right here is going to be a crazy decimal. I looked this up beforehand so we would know what it is. I put it in my calculator right here. What in the world happened to my calculator? 4 times the square root of 2/2 is approximately 2.8. Okay, so I'm going to fill this in as 2.8 and we'll plot. So go to pi over 4 and go 1 circle, 2 circles, about 2.8 is, I would say, about right there. Plot that point. And I also looked up what 4 times the square root of 3/2 is. That's the value. What would we round that to? Approximately 3.5. I'm going to say that's approximately 3.5. Let's fill that in right there. And so at pi over 3, I'm going to go to 3.5. 1, 2, 3. Here's 3.5, give or take, about right there. Now this value would reduce. That's 2, so it's 4 times 2 divided by 2. That becomes just 4. At pi over 2, go to the fourth circle. 1, 2, 3, 4, plot a point there. And now I can see what's happening. These are going to repeat down. So let's see if y'all are catching along. Because sine increases at the same rate, decreases here at the same rate. What's this value going to be? Shouldn't say at the same rate. The square root changes at the same amount. What's 3.5? Good. So at 2 pi over 3, we go to 3.5 again. This value is going to be approximately 2.8. Let's plot that one again. 1, 2, 2.8. This value is going to be 2. And this value is going to be 0. So if we've drawn this perfectly, you know what shape we should have gotten? A circle. Let's see how well we did here. If I plotted those right, I should have gotten a circle. Did we get a circle there? Yeah, we did. Now here's what's crazy. If I start going through these values, so I have a circle so far. Everybody sees that? Now I'm going to go over this in blue. If I started reducing these values are exactly the same, except they're now negatives. So I now have a -2. So let me remind you, if we're looking at the angle 7 pi over 6, and you have a negative radius, what do you do with a negative radius when you're looking at the value 7 pi over 6? You would go back the opposite way. So this point would be plotted right there. Look at that point. That's exactly on top of this value. 7 pi over 6 gets plotted right on top of 1 pi over 6 because this was a -2. This is a +2. They're opposites on opposite sides of the graph. So they go right on top of each other. Opposite radiuses on opposite side of radians will plot right on top of each other. Okay, what about this value? Guess what we get here? -2.8. And guess where 5 pi over 4 is? Exactly the opposite of that point. So do you see how this works? The second time as I go around this, these points would plot right on top of the points we already have. So at 3 pi over 2, we'd go plot at -4, which is right there. And whoops, I should have done a squiggly. This is again -3.5. So all these values are getting duplicated. So what does that mean for us? What it means is this graph could have been graphed within 1 pi of domain. There's our points there. This circle, we'll put the name of that as a circle, could have been graphed in 1 pi of domain. How much domain did I need to actually get the whole circle on the graph? How far in the table did we need to go to get the whole circle? It only needed 1 pi. Domain needed here for the full graph. Domain needed, I'm going to put, this is going to come in later. That's why I'm kind of hitting this. The domain needed is just 1 pi. So 0 to 1 pi is all I needed. Once I had those values, actually, I didn't even need to put a bracket there. I completed it, or we already had that point. Once I hit that point, we had the full graph already. So, polar graphs. Does this look, here's a question for you. Does this look like a function? No, but it is a function. And I'm going to show you why in a moment. Okay, let's do part B, and then I'm going to move on. Let's graph this one. We're going to sketch the graph of -6 cosine. So again, I want you to think through the unit circle. Cosine at 0. If you plug in a 0 to cosine, is cosine at its maximum, minimum, or is it a 0 when you plug in 0 to the angle here? Is cosine at x, is the x at it when you plug in a 0, is it at its maximum, minimum? Where is it at? You think of a unit circle, still a little too quiet around here. Is the x value right there? Is the x value, cosine's x, is it at its maximum, minimum, or what? It's at its maximum. It's at the value of 1. When I plug in a 0 there, I get 1. This is -6 times 1. That's what it is. Now, I could do it as the square root of 4 over 2. I'll write it like that. What is -6 times 1? -6. Now, this one's going to get plotted at what's going to be the furthest to the left. 1, 2, 3, 4, 5, 6. Why? Am I in the right spot? 1, 2, 3, 4, 5, 6. Right there. There we go. That's on the 6th circle. Wait, why did I just go left 6 units? Does negative always go left? No, for R, it goes, when you do polar, it goes away from. So I went 6 units left. Okay, now cosine's pattern, if you remember, is just like sine. So it's going to count down. If I start here at the square root of 4, I'm going to go square root of 3. And then it'll be the square root of 2. Let's just go ahead and fill in all of our numbers all the way down. I think it'll be quicker this way. So I'm going to fill in cosines. Remember, they follow this pattern. Whoops, forgot the 1. This takes a while. Almost there. Don't quit on me. And finally, we made it. And I need to find out what some values are. Real quickly, I'm going to type those in the calculator. I haven't done that yet. I'm going to need to know what the value times the square root of 3 over 2 is. And what the value of... So there's that one. And let's do this again. Whoops. I'm going to do this again where I change this to a 2. So it looks like -6 square root of 3 over 2 is going to be -5.2. And this is about -4.2. Okay, -5.2 and -4.2. That's what I'm going to reduce these to. So this is a -5.2. This one's going to be a -4.2. Okay, and the rest will simplify well. So at pi over 6, here's pi over 6. We need to go 5.2 circles the opposite direction. So 1, 2, 3, 4, 5.2. Plot that point about right there. And then at pi over 4, you go 4.2 circles the opposite direction away from 1, 2, 3, 4, 4.2. Let's just say that's about right there. And now these should reduce well. What's -6 divided by 2? Ignore the multiplying by 1. What's -6 divided by 2? -3. So at pi over 3, we go 3 circles away from it. 1, 2, 3. It should be right there. This value is going to be a 0. This value is going to become a +3. 1, 2, 3. This one is going to be, where are we? +4.2. The two negatives cancel each other out. So +4.2. 4.2. 2. And this one's going to become positive 5.2. Once I get all the way around here to pi, at pi, I get the value positive 6, which is right back here. At pi, I'm at positive 6. So notice I'm landing on the same exact spot, which means I only need one whole pi to plot this graph as well. So what is this? What shape did we just graph here? We graphed a circle again. Again, this is a circle. And just to add it in, how much domain did I need to graph the whole thing? How much domain do we need to graph this whole thing? Just 1 pi. What in the world? So let me add this in here. Domain needed. How much domain do we need to graph that whole circle? 0 till when did I complete the circle? Someone say pi. Pi. Okay. Sometimes here's what I want to hit at the start end. We'll hit this more at the end, but I want to give you some of the math now. Sometimes the graph will need all 2 pi. Sometimes it'll only need 1 pi. Here's how you know. Whenever you check, depending on the trig functions, maximum and minimum values, the maximum for cosine, think of cosine here. When is cosine at its maximum? What angle is that? That's cosine's maximum because cosine's x. 0. When you check its maximum versus its minimum value, if your radius is exactly the opposite, you only need 1 pi. Do you see how these are exactly the opposite? Do you see this? That's the maximum value here. That's the minimum value. I should say maximum minimum. That's based off a parent function of trig of cosine. Based on this equation, this is actually the minimum. This is the maximum. Tell me about the numbers. Are they exactly opposite of one another? Someone say yes or no, please. Are these 2 numbers either opposite or not the opposite? They're opposite. If they are the opposite, you only need 1 pi to complete the shape. Let's go back to the first one here. Was the maximum 0? Someone say no. No. What was the maximum number on there? 4. Now, that's at pi over 2. Where should the minimum occur? 3 pi over 4. Are those opposite of each other? Yes. If it's opposite of each other, you only need 1 pi to graph it. Whereas if they're not opposites, then you're going to need more than 1 pi to graph. Okay, I don't know if that makes sense to you yet, but we'll see that as we go on later. I just want to show you from the table. So that is the traditional way of graphing a polar equation. What do y'all think? Fast, slow? It's extremely slow. That's not the way I like to graph it. So here, this is not the traditional way, but I'm going to show you in a second after these DOLs, the best way, I believe the best way to graph a polar equation. So first, before we get there, got some DOLs. These are over the 2 problems we just did, okay? I want you to try to answer these questions. So now let's go on to example 2. On example 2, I'm going to give you what I believe is a much better way of graphing these functions. So if you had to sketch a polar function, this is what polar looks like. My recommendation is actually to use the normal rectangular version of the graph, like what we've been working on all unit 3. So notice, what did I change going from this equation here to this equation over here? What have I changed? Instead of r, I replaced the dependent variable with y, and instead of theta, I replaced it with x. Okay, let's think through first the beginning of unit 3. What would you tell me that value of 4 represents? This 4. Oh, that 4 is going to be the amplitude. Good thought on that. That 4 that's attached to the cosine of the amplitude. What do we call this 4 all by itself? Midline. That's the midline. Go to your graph, use your ID or something similar, and I want you to add a midline at y equals 4. Something like that. That's the midline. That was the midline. And as stated earlier, 4 is going to be our amplitude. Now remind me, does cosine start at its maximum or start at its minimum? I'm sorry, I said that wrong. I meant to say, does it start at the midline or does it start as maximum? Cosine starts at the maximum. So go up 4 units. 1, 2, 3, 4. Place a dot at 8. Now, I only focus on 4 points. I put them on your graph for you. These are the only 4 I focus on. So I want you to think through unit circle here. I'm only focused on what we call the quadrantal angles. 0, pi over 2, pi, and 3 pi over 2. And then finally, if you go all the way around, 2 pi. Those are the only ones I'm worried about. So I have 0 on there. Now tell me about cosine. What happens to cosine when you get to pi over 2? Tell me about the x. What's the x value once we get to pi over 2 here? 0. So at pi over 2, it actually reaches what we call the midline. At pi over 2, it reaches its midline. So put a dot there. Now, what happens when you reach 1 pi on the unit circle for cosine? It's the minimum. So when we get to the minimum here, I now go down 4 units, and I'm going to hit this pi right there on the x-axis, which we're going to see in a minute. It's going to represent the pole. Now, as I continue on the unit circle, what's the x value when I get to 3 pi over 2? 0. Well, in this case, it's going to be 4 times 0 plus 4, so it's back to the midline. And then finally, what happens when you go all the way around 2 pi? Back to the max. So I go back up to 8. Now, this should look like a wave that's connected. If we want to be really accurate, there's one more thing you can do on your value to think through this. I'm going to put the halfway point between 8 and 4, which is 6. Where does the graph hit? It doesn't do it like a line. Go with your hand real quick. Hand trick here, question. I'm going to do basically the inverse here. So take a look at the back of your hand. If you wanted cosine to be a half, which finger would you need to bend looking at the back of your hand to make cosine a half? Which finger do we need to bend to make cosine a half? Index. So now flip back over your index. What is your index finger? Pi over 3. Now, pi over 3 is right, it's this line. This is pi over 3. That means it'll be at the halfway point, 1 off of the zeros. So I'm going to go over here to this halfway point. This will help me out in graphing. Over here, it's the same thing. Off the zeros, it's going to be those points to help me make my wave. So now I'm going to connect it. So all that to say is waves are not V's. They should not look like a V. They should look like a wave. So I put that halfway point to help me better draw my wave. See how that looks like a wave, not a V now? I just realized that my halfway point in between the maximums and minimums and the zeros are closer to the zeros than they are the maximums and minimums. That's all that was to help me graph it properly. Okay, so let me translate this. Now that we have the graph, this serves as our full table. That is the full table of 2 pi right there. That's going to serve as our table. We're going to get our values from here. So how does this work? The x-axis represents the pole. If you're above the pole, you go towards the angle. If you're below, I said that wrong. If you're above the x-axis, above the x-axis means you go towards the angle. If you're below the x-axis, you go away from the angle. This graph will never go away from the angle, but it will hit the origin right there. That's going to hit the origin on the polar graph. So here's how we begin. At 8, we begin, I'll do it with the red circle, 8 circles out. 1, 2, 3, 4, 5, 6, 7, 8. Place a dot right there. Now, the next dot I'm going to place, I'm going to skip all these decimal values. I'm going to place this one here. What value did we say that was? Pi over 3. At pi over 3, I'm going to place a dot at 6. At pi over 3, I'm going to place a dot at 6. That's where that point is there. 6 comma pi over 3. Okay. Now, at pi over 2, we are at 4. I had that one in blue, so 1, 2, 3, 4. Place a dot there. That's 4 comma pi over 2. Pi over 2. There we go. The next one I had is this one here in green. Kind of got covered up. Let me plot those back on so you can see them again, where I'm getting these points. This is 2 pi over 3. At 2 pi over 3, we are at 2. At 2 pi over 3, we're on the second circle. Plot that one right there. Now at pi, we are at 0. That means we're on the pole. At pi, we are on the pole. You know what? I'm going to change this one to black so it stands out. We are on the pole at pi. And now I come back around. This is again the pi over 3. So at 4 pi over 3, I have a value at 2. At 4 pi over 3, here's 4 pi over 3, I go to 2. I would place that point right there. At 3 pi over 2, how many radiuses out am I going to be? 4. At 3 pi over 2, I go 4 radiuses out, and I'm going to place that point right there. This is another pi over 3. We'll be at 6. The next pi over 3, I'm at 6. 1, 2, 3, 4, 5, and 6. Plot that point there, and I'm going to skip these decimals along. Now we're going to connect all of our points. So we're going to connect our points. Notice this graph needed a whole 2 pi to make the cycle around. This one needs the whole 2 pi. So I'm going to try to connect these as best I can. It would be rounded out. I hit that, and then it bounced back out like this. And I heard someone whisper heart. You are correct. It hits this name from the Greek word. I think it's Greek, maybe it's Latin. The Greek word for heart. So the shape here, name of the polar curve, the general name is limacon for the equation. But more specifically, it is a cardioid. Cardioid, you've probably heard the word cardio before. Has to do with, I think it's Greek, maybe it's Latin, you can look it up later. Happens to do with the Greek or Latin word for heart. Because what did the graph look like? Heart. So the equation form falls under what we call a limacon, is how I should say. It's French. It's a French guy. But within the limacon family, so I'm about to show you 3 different limacons. A limacon, by the way, means snail. And this doesn't look like a snail, but the next one will. It's called a cardioid. Cardioid is going to be the important word for you. How can you remember cardioid? Cardio sounds like what you do for your heart. And what does the shape look like? A heart. Very good. Now, we plotted that a lot faster. How were we able to plot that a lot faster? Because we used the graph. Now, I do understand it takes some time to figure out what I'm doing on this graph. I get that. But you can go a lot faster once you figure out how this works than you can from the table. So let's reload and do it again. I got, I think, 3 of these in a row for you. So you get to see it 3 times in a row. All right, let's graph this one. Again, if I have to graph this polar function, what I would recommend for you, if you're on the test, is to quickly do a graph on the X and Y axis like this. So if I were to graph this one, what's the midline? 2. The midline is 2, and what is our amplitude? The amplitude is technically positive 5. Remember, amplitude is always positive. The negative will mean something. So go to positive 2, add your midline. Positive 2, add your midline. Now tell me about sine. Does sine begin at its maximum, or does sine begin at the 0, the midline? Sine is y, so when we begin here, sine is at its midline or its 0 value. So we're going to begin right there. Put a dot right there. So at 0, let's translate this. Now I'll do all the points at once. Sorry, we'll start there. Now sine typically gets to its maximum at what value? Pi over 2. Now this problem, because it's negative, doesn't go to its maximum first. Rather, it goes to its minimum. So at pi over 2, we need to go down 5 units from here. So 1, 2, 3, 4, 5. Put a dot right there. Now, when will sine return back to its midline? When does sine get back to its 0 value on the unit circle? At pi. So at pi, it gets back to the midline. Let's put another dot there. At pi, it gets back to the midline. Now, when does sine normally get to its minimum? Okay, when does sine get to its minimum normally? Whoops. 3 pi over 2. Well, in this case, because of the this transformation, it's not a minimum, it's actually going to become the maximum. Let's add 5 units. So at 3 pi over 2, we add 5. 1, 2, 3, 4, 5. And then it'll return back to the 0 value once it goes full circle, which is how much? 2 pi. So add another midline point at 2 pi. To fill this in, the halfway points, meaning the halfway between the top and bottom, they always occur closer to the 0. So if you want to draw your wave right, it's not going to be closer to pi over 2 this time. It's going to be closer to 2 pi's. The halfway point will be here. Let me change that to green. The halfway point will be, what's half of 5? 2.5. The 2.5 is going to happen there and there. Next to those zeros, same thing. Next to this, I said zeros. I meant to say midline. Next to this midline, if you want your graph to look right.
Where'd you get the green dots?
Okay, so the halfway point, it might be easier to show you here on the tables. The half, whenever you have a half, that's always the half value, half of the amplitude, always comes next to the 0 of the trig function. So I'll say it again. Sine has its zeros at pi over 2 and 3 pi over 2. You following with me? Sine at pi over 2 and 3 pi over 2. That means the halfway points are going to be just to the side to the pi over 2's, which in this case would be a pi over 3. You see how that's a 1/2 right there? Pi over 3, and 2 pi over 3 is also a 1/2. Jump down over here. This pi over 3 and this pi over 3 on either side of 3 pi over 2. Notice, see how those are 1/2s as well? That's where the half values come from. Now, if it were cosine, whoops, cosine has its zeros at 0 and pi. So the half values come at pi over 6 because they're on either side of the zeros. I don't know if I'm making sense to you. Am I making sense at all? Let me come back to this graph. To make my wave, how many zeros do you see on the graph? How many zeros do you see on that graph? 3. The halfway points come closest, not closest to the maximum and minimum. They come closer. They're leaning closer to the zeros like that, to the midline, if you will. So you see how I didn't put them in the middle? I did not put them in the. You could do the math hand trick, but I'm just telling you by pattern where they'll be. Let me play around with it for a second. What if I did it incorrectly? What if I put these green dots closer to the maximum? Would that look like a wave? No. So to make it look like a wave, those points have to be closer to the midline points like that. So when I connect it, you'll notice this won't look like a wave. It's going to look like, I said that wrong. It will look like a wave. It won't look like a V. So when I connect these points, it goes like this. You see how it looks like a wave? So the halfway points are not centered on sine and cosine. They're always shifted closer to the to whatever radian gives you the midline points. Am I making sense to you at all? Okay, just keep tracking and we'll see if we get there. Let's plot these points. So I begin remember, if it's above the x-axis, that translates to going towards the angle. If it's below the x-axis, that translates as going away from the angle. And finally, if it hits the x-axis, that means you're going to hit the, what do we call it on this graph? The pole. We're going to hit the pole. Okay, so let's graph this. The first point is 2 units away from the angle 0. So go away from towards 0. Sorry, 2 units towards 0. Right there. Plot a point at 2. The next point I'm going to graph is pi over 6. This is pi over 6 here. That's pi over 6. At pi over 6, we are at a value of what? -1/2. So at pi over 6, we're at -1/2. Go away from it about right there. Plot that point. That's negative half at pi over 6. At pi over 2, here's pi over 2. What's our value going to be? Negative 3. So go 3 units away from it. 1, 2, 3. Now, so far, my graph is going this direction. It's going like this, and it's hooking back this way. That's the order. As I go around, that's what's happening. Okay, now I get up to here. This is the next pi over 6. The next pi over 6, which is 5 pi over 6. This is 5 pi over 6 right there. Are you tracking with why it's 5 pi over 6? This would be 2 pi over 3. That would be 3 pi over 4. This is now 5 pi over 6. At 5 pi over 6, we're at negative 0.5. 5 pi over 6, here it is, negative 0.5, which is really close and tight here. Okay, at 1 pi, what value are we at? 2, which is over here. So you're going, what in the world does this look like? I'm about to show you. Okay, this is the next pi over 6, which is 7 pi over 6. At 7 pi over 6, what's our value there? 4.5. 7 pi over 6, we go 4.5 towards it. 1, 2, 3, 4, 4.5. So what has happened so far is that we've started plotting it. We've connected to this point, and then it went to this point. Whoops, I didn't curve that very well. That's why I go to my board when I do this. Went to this point, and then I went to this point, and then I've come out to this point here, and now I'm making my way around. And then I'll come to this point here. Okay, I'm going to continue on. That was 7 pi over 6. My next point is 3 pi over 2. At 3 pi over 2, we need to go 7 circles. So at 3 pi over 2, I go 1, 2, 3, 4, 5, 6, and 7. Plot that point right there. My ink's running out, apparently. There it goes. And so this would wrap around like this, and it would come back here. Like that. That's kind of ugly. And coming back down, what pi over 6 is this one? 11 pi over 6, we are at 4.5. At 11 pi over 6. At 11 pi over 6, we're at 4.5. 1, 2, 3, 4. That must be 5, so it's right in there at this spot, and we'll connect them. Do this. I think I'm more accurate when I use this. Like that. That's what the graph should look like. Okay, let's make some observations. I didn't do this with part A. Why do you think this shape here, I'll give you the name, so you're probably wondering it. This is called a limestone as well. Again, it's in the family of limestone. Whoops, that's not how you spell that. Take away the I. This is also a limestone. But within the family, they call it a looped limestone. Why do you think they call it looped? What does it have in there? A loop. Now, what do you think makes this looped limestone face down? There's two things that make it go face down. Why? The negative is important. There's something else that has to be with it to make it go down, though. The sign. Because it was a negative and a sign, it faced down. Now let's make some observations. How far down did it go? What was the lowest point? 7. Why? Because signs, maximum and minimum, is range. Just sign by itself can go as high as 1 and as low as -1. At its maximum, you're multiplying by 1, which means it's a -5 times 1, which is a -5, and then you add it to 2, and you got the value 3. At sign what's normally its maximum, pi over 2, it went down to -3 because it was 2 minus 5. That's what happened mathematically. Whereas this bottom point actually occurs at 3 pi over 2 when sign's at its minimum. What is the sign's minimum again? What is sign's minimum? Negative how much? -1. So it became 2 times -5. Excuse me, 2 minus 5 times -1. That becomes a positive 5. What's 2 plus 5? 7. Okay, now all this I know can be tricky. So I've done something to help you out. On Google Classroom, I programmed something to help you see this. And I'm going to type this equation in. What was the equation we were working with? 2 minus 5? Is that what we were working with? Okay, so I want you to see this as it plays out as I go around. I'm going to change my angle here, and you'll see it as I go around. This shows me where my angle is. This traces the graph as I go around. You see, as we move around the circle, why do you think at 11 pi over 24, or let me go to a value you're used to, pi over 3, why at pi over 3 am I on the opposite side of the graph? Because r is negative. R is negative on these points. But as you go around, you start to see that once it turns this point, the R is actually positive because you see how this point is facing 13 pi over 12? See how it's coming towards it? So my R is now positive. My R value is now positive, and my R value stays positive. Even though the graph is facing down, my R is positive because this point is coming towards the pi as I go around. Does that make sense how that works? You can, if you get lost, you can use this to help you out as a tool. I attached it in Google Classroom. Let me ask this question. How much domain was needed to graph the whole shape? Could I do this in 1 pi, or did I need all 2 pi? You needed all 2 pi. You needed all 2 pi, which means at its signs maximum and signs minimums, the values were not opposites. At signs, what's signs normal of maximum, I had a -3, -1, 2, 3. See how that's a -3? But at signs minimum, which is 3 pi over 2, the graph itself had a value of +7. Is -3 the opposite of +7? No, and that's why I needed all 2 pi. We could have done this on all the previous graphs. You see how that looks like a snail? Let me flip it around. See how it looks like a snail? If you're into Mario, you might think it looks like Toad there. Maybe it looks like Toad. Limacon means snail. That's why they call it a limacon. But the family has 3 different looking graphs. Limacon is anytime it's A plus or minus B sine or cosine. That's what makes it a limacon. Okay, I got one more for you. Let's see one more. Let's see if we can speed through this a little faster. Tell me about if I wanted to graph this, and I'm going to use a normal graph. What's the midline? 5. Midline is 5. What's my amplitude? My P went out. There we go. Amplitude. Okay, so let's go to our graph. Let's draw a line at 5. Does cosine start at its maximum, minimum, or at its midline? Typically, it's maximum. This has a negative. What's that going to make it do? Start at the minimum. So at 5, go down 2 units. 5, go down 2 units, put a dot. Okay, as we go around the unit circle, I'll just use the circle over here. You're thinking about the x value. If I thought of it here, I'm starting at its maximum. Transformation makes it be a minimum. But when does cosine reach its 0 or its midline? Typically pi over 2. So at pi over 2, it should reach the midline. Put a dot there. At pi over 2, this should reach the midline. When does cosine normally reach its minimum? Someone say pi. Pi. On this case, it's not going to be a minimum, though, because the transformation, the reflection, it's going to make the minimum become a maximum. So let's plot the point at pi, go up 2. Now, when will cosine return to its midline? 3 pi over 2. And then what happens at 2 pi for this particular function? Minimum. Oh, I don't think I ever completed the loop on that. Okay. I'm going to talk about why is it a function here in a second. Now let's graph the halfway points. Remind me, do the halfway points. This is for Jesse. The halfway point between 5 and 3. Does it happen closer to the minimum, or does it happen closer to the 0? Or the midline, I should say. What do you think, Jesse? Closer over here? It's a good guess, but no. It's not closer to the minimum, it's closer to the midline. That's where you're looking. So it should be there and here, which means what hand trick, what's next to pi over 2? What's the finger that's close to pi over 2? Pi over 3. This is going to refer to pi over 3, and this one would be 2 pi over 3. And I'll do the same thing over here. These will be pi over 3s as well. What pi over 3 comes next? 4 pi over 3, followed by the last one. 5 pi over 3. Okay, those are our values that we're going to hit. Okay. Now, will this ever hit the pole, meaning the origin on the polar graph? Will this ever hit the pole? You should say no, because what does this graph never hit? The x-axis refers to the pole over here. Since it never hits the x-axis, it'll never hit the pole over here. So let's graph. Starting at 0, we're at 3. So this one might be a little bit easier for you to graph going around. At 0, we're at 3. 1, 2, 3. There's a point. At pi over 3, we're at 4. It's in purple. Pi over 3, we're at 4. 1, 2, 3, 4. At pi over 2, we're at 5. In black, pi over 2, we're at 5. 2 pi over 3, we're at 6. 2 pi over 3, we're at 6. At 1 whole pi, we're at 7. 1 whole pi, we're at 7. At 4 pi over 3, we're down to 6. 4 pi over 3, we're down to 6. 3 pi over 2, we're down to 5. Let me scroll down so you can see the 3 pi over 2. We're down to 5. 5 pi over 3, we're down to 4. Purple again. 5 pi over 3, we're down to 4. And then finally, if we went all the way to 2 pi, we're back at 3. This right here is what you call a dimpled limacon. Limacon, I should say. It's a dimpled limacon. It looks square. I shouldn't say square. It looks flat. It looks flat on one side. You see how it looks really flat on that side? The left side seems pretty rounded, but you see how flat the right side is? That's what we call a dimpled. They could call it convex. But that's a dimpled limacon. Again, it's the limacon family. That just means the equation's in the form of A plus or minus B sine cosine. Dimpled limacon. Within the limacon family, it's a dimpled limacon. So what's it mean if it's a cardioid? What's it going to look like? A heart. It'll have that crack that you think of with a heart, how it comes to that point. Okay, it'll have that. A limacon that's looped obviously has an inner loop, and a dimpled or convex will be pretty flat on one side. That was a lot there. All right, we have some DOL questions to see if you grasp what we've done so far. Oh, no, I'm wrong. I got one more. If I gave you a graph, I want you to do one this way. This is more of a review as anything else. We had to write an equation on this. What did you tell me about the equation just looking at the picture here? Wow, sine. How'd you know it's sine? It starts at its midline. Okay, so I'm going to call this y equals, just to stay same form, I'm going to say, is this a positive sign or a negative sign graph? Positive. So I'm going to skip a blank for a second. And the amplitude is how much? 2 units. So it'd be 2 sine theta over there. What's my midline? So then that would go on the front. That would be my sinusoidal equation. Earlier in the year, we put, oops, I messed up one thing. Very minor. Y'all see the very minor mess up I have? Has to do with my variables. Should be an X. Look at the axis. Does it say theta axis or X axis? X axis. There you go. Okay, question for you. Let's see before we graph it. Can you guess what type of shape this will be looking at this graph? First, will it ever hit the pole? How do you know it'll hit the pole?
Because it's crossing.
So what does that mean? What can it not mean? What can it not be if it does hit the pole? Which one of our three shapes did not hit the pole? Dimple. Can't be dimple. Okay, what's going to happen if you go negative like this? Negative sign, which is going to create a loop. It's going to be the looped one. Here we go. Let's plot it and see. We start at 0, 1. I don't know why I said 0, 1. That wouldn't even be right, even if I was on an X and Y. Well, yeah, that's right over here, 0, 1. But over here, I go 1 towards angle 0. Okay, here's a great point. What is half of pi over 3? That's pi over 6 right there. At pi over 6, we go to 2. Pi over 6, we go to 2. That's a weird decimal. I'm going to skip that one. This is pi over 2 right here. Pi over 2, we're up at 3. 1, 2, 3. At 2 pi over 3, that's going to be weird. The next one's going to be our 5 pi over 6. Notice our good values keep the same denominator. At 5 pi over 6, we are at 2. 5 pi over 6, we're at 2. Here, I'm going to hit the origin. Nope, I skipped one. At pi, we are at 1. Then it's going to hit the origin, which means over here, it's going to hit the pole at 7 pi over 6. At 7 pi over 6, we hit the pole. So far, we've come around here, and we're hitting the pole. And now I go negative. What value is in between 4 pi over 3 and 5 pi over 3? That's 3 pi over 2. At 3 pi over 2, we're at negative 1. What does it mean if it's negative? That's right. So I'm going to add in where we are on the graph so you can follow where this point should be. At this stage, we have started here. We went around like this. We hit the origin. So I'm now going this way. Make sense? Okay, next point is here. What's this value? Nope. Yeah, sure. It's a 0. Sorry. Radians. What's the radian count? 11 pi over 6. At 11 pi over 6, we have a value of 0. So it's right back there. Okay, so we'll finish off the graph. At this stage, all I would do is, oops, wrong color, is this would pick back up and connect like that. Hey, do I need all 2 pi or can I do this in 1 pi graph? We needed all 2 pi. We needed all 2 pi to get all the way around. Now, if you graph these as on the XY system, if you graph these on the XY system, you'll know if your graph's going to be repeating quicker just because of the values being perfectly symmetrical on the x-axis. Not symmetrical on the x-axis, I'm sorry. They would be centered on the x-axis. If you were going to get a the midline, it'd have to be over there for it to work, among other things. Oh, what's the name of this one? You already named it, but I didn't write it down. This is a looped limousin is how you would say it using the French. Okay, now we have some DOLs. I'll let you sort through some of these, come up with what you think. These 3 questions are asking you about A and B. Each one of them is talking about A and B. So if you look at the equation, what has to be true to make a cardioid? You can compare and contrast on the examples we've done. What has to be true of A and B to get you a cardioid? What has to be true of A and B to get you a looped? What has to be true of A and B to get you dimpled? Go ahead and do that, DOL number 2. All right, now we're going to switch gears and talk about symmetry. Now, there are some tests that we can do. Today, we won't have time to get into it, but I'm going to give you some visuals and you can see how we have symmetry with polar graphs. Polar graphs are cool in that you can have different symmetries based off of different things you're given. So here, let's do this. I'm going to have 2 different graphs here. Now, yeah, I'll do 2 different graphs. Okay, here's what this is saying. If you started with a r comma theta, I'm just going to put going this way. That is r comma theta. And now what do you do on a test is you're going to replace in the equation with r stays as r, but the theta becomes pi minus theta. So normally theta goes counterclockwise. You know how theta normally moves this way? What this is saying is you start from pi and you subtract theta. So mean we go this way. Now that right there, what I just did is r comma pi minus theta. Now what type of symmetry do these two arrows have? What kind of symmetry? Is it with the x-axis, y-axis, or the origin? The y-axis. Now, that's what we would call it beforehand. Go ahead, Destiny. But so here, we're going to say it's symmetry with respect to, in polar, you would call this pi, theta equals pi over 2. Now, the other way to look at this means this. Again, if this is r theta, that's your normal r theta. You go that way. R theta. What this one's saying down here is this says take a negative r, so you go the opposite direction as you go the opposite angle. So opposite angle means I'm going this way, but as you go this way, you actually go across the pole, and so you actually move this way like that. That right there is what it would look like. So normally we would go down for a negative angle, but because it's a negative radius, it goes across. Again, what do you notice about this symmetry? It's across the y. Yep, that's what's happening in those two pictures. That's the first and the second. Okay, the next one. For the sake of time, maybe I don't graph both of these. I'll just show you one because they're going to end up being the same picture. We want to look at r negative theta versus r theta. Okay, so again, here's r theta. Here is r theta. Well, what's different if you replaced theta with a negative theta? What does that do graphically speaking if you have a negative angle? You go the opposite way. It goes this way. Okay, so this is now r comma negative theta. If you have r negative theta, what type of symmetry is that? That's x-axis. What do we call the x-axis in polar? We call it the polar axis. You have symmetry with the polar axis. That's what you'd call that. So if it looks like the y-axis, you call it symmetry with respect to theta equals pi over 2. If you have x-axis symmetry, we call this symmetry with respect to the polar axis. Okay, finally, last one. Let's talk about this one. So here again is r theta. This is what r theta would look like. It would go this direction, r comma theta. Let's say we change the r to be negative. What happens if you have a negative r? You go across. So we'd start over here and I would work this way. So I go over here and I would work this way. So I go across the origin and then I keep moving the same direction. That would be right there, negative r comma theta. What kind of symmetry is that with? That's symmetry across the origin. Now, if you have symmetry across the origin and polar axis, we don't call it the origin, we call it the pole. You have symmetry with respect to the pole. Oh, I don't have to do the twice. The is already there. I guess I shouldn't have put a the there because this would not have a the, but I should have put the here and I should have put the there. There we go. That's how now I have good English. Here's what this says. If you test these by plugging in one might fail, but just because that fails doesn't mean it's not symmetrical. If you test the other might pass. If either one of these tests pass, then it's symmetric. Okay, so that's what that's saying here. If it passes, it's guaranteed symmetric. But if it fails, if one test fails, it doesn't mean it's not actually symmetric at all. Quick test. If you have sine, what do you think sine will always be have symmetry with? It'll always have symmetry with the sine is y. What do you think sine will always have respect to? What represents the y on polar axis? Theta equals pi over 2. Good. What about cosine? Cosine always has symmetry with respect to the polar axis, the x-axis, the polar axis. That's a shortcut. Today, that's all we're going to get into. Is we're just going to name the shortcut as we go, rather than actually doing the test. But there's the test that when we get more time, we'll spin. Okay, here we go. More graphs, but this time I'm going to speed this up a little bit. What we're going to see here is called a rose. Go down to your name. I'm about to graph what's called a rose. It's going to look like a flower. Okay, with a rose, here's what's really neat. That inside value there, inside the trigonometric function, that is what we call n. On this problem, n is 5. By rule, if you see down here, it says if n is odd, there will be n petals on this rose. If n is even, there will be twice as many petals. So is 5 an even number or odd number? Odd. That means this will have 5 petals. So now let's talk about where the first maximum would be, the first petal. Here's what you do. This is a sine function. Where is sine normally at its maximum? Where is sine normally at its maximum? Right there, max at pi over 2. So here's what you do. You take the inside, what's called the argument, and you say 5 theta equals pi over 2. This is how you find out where the petals occur. And I'm going to solve this for theta. What do I do to get this theta isolated since it's multiplying right now? Divide by 5. When I divide by 5, I get that theta equals, it's already being divided by 2, now it's divided by 5. Dividing by 2 and dividing by 5 is the same thing as dividing by 10. Now pi over 10 is somewhere in here. I'm just going to place it here. My maximum value should occur at, let me put this in parentheses, 6 comma pi over 10. Now wait a minute, where did this 6 come from? Right here. This value, it's like the amplitude. So I'm going to go 6 circles out. 1, 2, 3, 4, 5, 6. And I'm going to say pi over 10. That's 18 degrees. I'm going to say it's somewhere right in here. Pi over 6 I know is 30 degrees. Pi over 10 would be 18 degrees. I'm going to say it's about right there. Now, I'm about to walk you through what's going to happen here. To get to the first minimum, I have to cross over the pole. So I'm going to cross over the pole to get to the minimum. Its first minimum is here. Now, what is that value that gives you the first minimum? 3 pi over, 3 pi over 2. So the first minimum, here's how you solve that. You'd say 5 theta equals 3 pi over 2. Now I'll do the same math. To get theta isolated, I divide both sides by 5. And we get that theta equals 3 pi divided by 2 divided by 5 becomes 3 pi over 10. So my first minimum is going to occur at not positive 6, but negative 6, comma, 3 pi over 10. So be 3 pi over 10. Oh man, that would be 18 degrees times 3, 30, 54 degrees. It's somewhere in between these two. 3 pi over 10 is somewhere over here. I'm just going to put it approximately right there. But it has a value of negative 6, which means I do not go 6 circles towards it. I go 6 circles the other way. So I'm coming back this way. 1, 2, 3, 4, 5, and that's 6. It's going to be in between these two. I'm going to place it about right there. Now you might be looking going, how is this graph going to look? Well, I'm about to show you as I go. First, let's get to here. Maximums and minimums repeat every, well, it should repeat, sine should repeat how often? Every 2 pi's, right? To get it all the way around. So what we're going to do is we should be 2 pi's, but we're going to set this 5 theta equal to 2 pi. And when you divide by 5, what do we get? Okay, so every 2 pi over 5, I should have another maximum. Every 2 pi over 5, I should have another minimum, which is the same thing as 4 pi over 10. So what am I saying? If I had a maximum at 1 pi over 10, the next maximum, 2 pi over 5 is like 5 pi over 10. I'm going to change this to 4 pi over 10. The next maximum would occur at 5 pi over 10. 1 pi plus 4 pi is how many pi's? 5 pi over 10. I'm going to have a maximum here. And then I'll have another minimum if I took this 3 pi and add 4 pi. What's 3 pi over 10 plus 4 pi over 10? 7 pi over 10. That's 7 pi over 10, which is in here, I think. 7 pi over 10 should be over here somewhere. It would reflect across, and it'll have a negative somewhere over here. Now, I'm going to get all off if I'm not careful. So I'm going to start drawing this, and I'll show you on the graph what happens. So here's how this rose is going to look. We're going to begin, and it's going to go like this, and then it's going to come back to the pole because we're now going to go to its negative. So it comes around this way. And it comes back up, and it goes like this. And it's going to keep going around. You see how it's making like a rose? That's what happens here. So now let me flip over so we don't make a mistake. Let's just go over to Desmos real quick, and I'll show you. The equation was 6 sine 5 theta. Okay, let's start from 0. Here we were. We went out. That first maximum occurred at pi over what value? Pi over 10. You see how, what is pi over 10 in between those two? Yep, and so you would keep going around. It would hit the pole, and it would head to its first minimum. Where do we say that minimum is? 3 pi over 10, which that's right in between here. It's right in between there. We get to 3 pi over 10. And then we came up, and we had its next maximum at 5 pi over 10, which reduced to become pi over 2. Your next minimum is over here, which we didn't put that on the graph. That was the one I was missing. Let's go over there. That's in between 5 pi over 3 and 4 pi or 7 pi over 4. Let's put that one on there. This would be the next minimum. It would be right in there. And then finally, the last piece I'm missing is going to be this one right here. And this would be a maximum at 9 pi over 10. At 9 pi over 10, we'd have a maximum, which is over here. So if I continued on this graph, this would go this way. It would hit. And then it would come back out to a maximum like this. Now, this graph completes in 1 pi. This completes in 1 pi. This graph would complete in 1 whole pi. What type of symmetry does this graph have? Does it look like x-axis, y-axis, or origin? The y-axis. It's reflecting on the y-axis. And so what do you call that in polar? We don't call the y-axis. What do we call it instead? I'm going to say with respect to theta equals pi over 2. Why did it have symmetry with pi over 2? Why with pi over 2? I got only one person who's speaking up. Why was it symmetric with pi over 2? It had to do a whole 100% with the equation. With sine. Sine is what variable again? Y. And the y-axis is theta equals pi over 2 in polar. Okay. All right, let's look at one more. I got another rose here. What about r equals 8 cosine 2 theta? Okay, on this one, what is n? 2. 8. How many petals would it then have? Remember, if it's even at doubles, you'd have 4 petals. 4 petals. Let's talk about the first maximum on cosine. Where should cosine receive its first maximum? Cosine's what letter again? X. Where should cosine's first maximum occur? At 0. So this one's going to be really easy to solve. What is 2 pi? Or, excuse me. What is 0 divided by 2? We have its first maximum at 0. So if you go out at 0, we have its first maximum out at 8. Okay, where would cosine's first minimum occur? Cosine's first minimum is supposed to occur at where? Pi. So how you'd solve this, you'd say 2 theta equals pi, and now we solve for theta. How to get theta by itself? Divide by 2. That means at theta equals pi over 2, we have its first minimum. Now, what's the minimum of this cosine or this graph? Negative how much? Should be putting this in parentheses. Negative 8 at pi over 2. So this point was, let me do this one green. This one was positive 8 at 0. Positive 8 at 0. The minimum is going to be negative 8 at pi over 2. So at pi over 2, we go down negative 8. So the maximums and minimums would repeat every, now cosine, what's its period? 2 pi. So what you do is you say 2 theta equals 2 pi. How do you isolate this? Divide by 2. And so those cancel. Every theta equals 1 whole pi. So if I had a maximum at 0, I will have another maximum at positive pi. That would be another maximum. If I had a minimum at pi over 2, I'll have another minimum at negative pi over 2. So the petals will go out to those points. So how does it work? Because this is a maximum and this is a minimum here. Maximum, these are minimums. You have to go through the pole to arrive at each one. So what does that make the graph look like? It comes out like this. It heads back around. It goes down here. Back around. It would hit this spot. It'll come back around this way. And then it comes back here. I know it looks messy, but that's how it looks. If you don't believe me, let me just show you right here. 8 cosine 2 theta. Don't just watch my shape. Watch the order here. What happens? We start here. What happens? The graph goes around. You see how I went through the pole? Now I'm heading towards the minimum. Hit the minimum, come back through the pole. Now I'm going to the maximum. Through the pole, now I go to the next minimum. And I'm back around towards the maximum at 2 pi. That would be the path you would take to get there. You can use that. What type of symmetry does this graph have when you look at it? Does it have polar axis? Does it have theta equals pi over 2? And what about the origin? It would be all three symmetric. What's the name of this graph, by the way? This is a rose.
If it's an even number, put it on.
Twice the petals. Now let's you take a look at this DOL. All right, let's now take a look at example 4. So earlier I was talking about is what's required. When do we need a full 2 pi? When do we not? Well, graphically, you can solve some of this if you were able to look at the graph, the rectangular graph, the y equals 3 plus 3 cosine x. You can figure it out pretty easy. But on this one, what you can do is if you just compare what appears to be the maximum and what would be the minimum, so in this case it's cosine, you need to have exactly the opposite values. So cosine has its maximum at pi, or 0, excuse me, and its minimum at pi. So if I check, what I want to know is the value of 3 plus 3 cosine of 0. I want to know if it's exactly the opposite of 3 plus 3 cosine. Now remember, cosine's minimum occurs at pi. That's what I want to know. If they're exactly the opposite, it only takes 1 pi. If they're not, then it takes 2 pi. So here, if I go to reduce this, cosine at 0 is 1. So it's 3 plus 3 times 1. 3 plus, let's change colors, sorry. This would be 3 plus 3 times 1, which is equal to 6. So that's where that point comes from there. Okay, and I'll do it again down here now. Now we're at cosine's minimum. So this would be 3 plus 3 times negative 1. Well, that is 3 minus 3, which is 0. You see how these are not opposites? So we need to fold 2 pi. We need 2 pi. And there's no domain restriction. We need the whole thing. Okay, now let's check this one, 4 sine 5 theta. Now sine has its maximum. Again, this is based off of the max and the min, the maximum and min values for the parent function. Okay, that's what I'm doing here. So I'll do it again here. This time, maximum for sine occurs at pi over 2. So we're going to look at 4 sine of 5 times pi over 2. And then r equals 4 sine. The minimum occurs at 3 pi over 2. Okay, so we go to simplify this. This would be 4 sine of 5 pi over 2. And this one would be 4 sine of 15 pi over 2. Now, because those are beyond one whole unit circle, I'm going to reduce that by using coterminal angles. 5 pi over 2, if you take away 2 pi, it's like taking away 4 pi over 2. That is 4 sine of 1 pi over 2. And this would be equal to, sorry about that. Okay, so 4 sine, what in the world? Okay, let's try this one more time. 4 sine, there we go. 15 pi over 2, that's like 7.5 pi. Take away 2 pi, we now get, it was 7.5 pi, now you get 5.5, and you take away another 2 pi, you get 3.5, and you take away again, you get, wait, what am I doing here? I'm getting something wrong. Not 1 pi over 2. Let me see, think about this. Take away 4, it's 11, take away 4, 7, take away 4. Yeah, 3 pi over 2. There we go. 3 pi over 2. It's doing bad math. So those are just coterminal values. Now what you'll notice is at pi over 2, sine is 1. So this is 4 times 1, which would equal 4. Right, min. I never wrote min down here. So this would be 4 times 1, which is simply just 4. This is 4 times -1, which is -4. Do you see how those are complete opposites? Because these are exactly opposites, we only need 1 pi to graph this. We only need, here we go, 0 to 1 pi. Now I'll show you graphically. So we're going to graph both of these over here. Come on now. Don't freeze up on me now. 3 plus 3 cosine of theta. As you see this graph, it's going to need all 2 pi to go around. You'll see we do not complete the shape until we go a full 2 pi. But on the next graph where we looked at 4 sine 5 theta, let me change this to a sine, you'll see it'll only take 1 pi going around the circle before we make the whole shape. So here we go. So there's 1 right there, petal. Now I've done 2 petals, 3 petals, 4 petals, and here's the 5th petal at pi. We've completed the whole cycle at pi. And if I went to 2 pi, it would highlight over where we've already been. So this one only needed 1 pi to go around the circle. So this one, it's only 1 pi. Okay, here, by the way, by rule, if it looks like one perfect petal or circle on like an odd number petals per, it's probably going to be just 1 pi. If it's not a perfect looking petal, or if it's an even number, then it'll probably need 2 pi. That's just kind of a shortcut. So on this one, if you count them up, 1, 2, 3, 4, 5, 6, 7, 8. Because it's 8, I would guess it's going to need 2 pi. I'm going to guess it needs 2 pi. Now, again, what you could do, because this is a cosine, is you just plug in the maximum minimum values. So the maximum for cosine should occur at 0. So it would be 3 cosine 4 times 0, which that could simplify to be just 3 cosine of 0. Whoops, theta 0. There we go. And if I simplify that, cosine of 0 is 1. 3 times 1 is 3. Now, if I try the minimum, I need this to be a -3. 3 cosine of 4 times, cosine gets its minimum at pi. So 4 times pi is just 4 pi, which is coterminal with 2 pi, which is also coterminal with 0, and notice here we get 3. Those are not the same value. I mean, those are not opposites, they're the same. So we need a full 2 pi. That means when we're at 0, we're over here. When we're at pi, we're over here. They're not in the same location. For that reason, we need the full pi. They're not opposites. Okay, now this one, see how it's a perfect circle or a perfect petal, like I said earlier, is usually this one I'm going to predict needs only 1 pi. So how do we predict? We plug in our numbers. R equals for cosine. The maximum I plug in is 0. That's where cosine gets its max. And its minimum is going to be when we plug in for cosine of pi. Now what you'll see is these are going to be opposites. So this is 4 times 1, which is just 4. This is 4 times -1, which is -4. Since they're opposites, you only need 1 pi. Here's 2 more. Okay. Okay, now let's finish up example 5 here. When we get to that, it's talking about finding points of intersection. So I have 2 different graphs here. I have a circle with a radius of 1, and I have this interlooped limosome, and I want to know where are these equal. And if I look at the picture, it looks like there's 3 points of intersection. It looks like there's going to be a point of intersection here, here, and here. That's what they appear to be. But common points mean those are common points, but they might not actually be solutions. So what we have to do is solve this. So what do? I plug in, I substitute. The shared variable here is r. So I'm just going to plug 1 in for this r. I'm going to substitute. I'm going to substitute this in right there. And so I have 1 equals 1 minus 2 cosine theta. And we're going to solve this. So if I solve, I would subtract 1 from both sides. And I have 0 equals -2 cosine of theta. Divide by -2. That doesn't change anything here. It just removes the -2 coefficient. 0 divided by -2 is still 0. So I want to know, where does cosine equal 0? Well, cosine's the variable x. So x has a 0 here at pi over 2 and 3 pi over 2. At pi over 2 and 3 pi over 2. So what does that mean? That means we have solutions at pi over 2 and 3 pi over 2, pi over 2, and 3 pi over 2. Those are my solutions. We have an extra common point. This common point would be left 1, or excuse me, a radius of 1 at pi, and a common point. We have an additional common point. So we have the common point at radius of 1 pi, and then these two where they intersect, which would be 1 comma pi over 2 and 1, whoops, let me rewrite that, 1 comma pi over 2 and also 1 comma 3 pi over 2. Those are the common points, but these are the only 2 solutions. Make note of that. The solutions won't always be where the graphs appear to intersect. Those could be common points, but not necessarily solutions. Okay, so if you plugged in the value pi over here on this graph, you would not get 1. If you plugged in a pi, you would get a value of 1 here, but you multiply that times -2, it's -2. 1 minus 2 is -1. So you notice that that's not equal. At pi, we have a value of -1. Pi, that's a -1, positive. No, I'm sorry, you get 3. So that's why that point is not actually part of a solution set, but it is a common point in the graph. Okay, part B, let's do this again. So if I want to solve this, I need to substitute for my r's. These are my shared variables. So I'm going to say 3 sine theta is going to equal 1 plus sine theta. And looking at the picture, we can see these common points. This has 2 common points there and there. We have 3 common points. Can't count. 3 common points. So how would I solve this one? Well, I'd combine my like terms. So those cancel out, and so I now have 2 sine thetas equaling 1. I divide both sides by 2. just doing basic algebra right now. And I have sine theta equals 1/2, and according to the unit circle, and you could do an inverse sine if you wanted to figure out what that value is, but I'm just going to use unit circle sine. Where is this the y value? 1/2. Well, using an inverse, that value right there would be pi over 6. If you use the back of your hand, you want one sine finger, you bend your ring finger, flip it over. That ring finger is pi over 6. That means you do have an answer at pi over 6. That's not the only place sine is 1/2. You also have sine of 1/2 over here at this pi over 6, which is 5 pi over 6. So our solutions are theta equals pi over 6 and 5 pi over 6. Those are our solutions. That's the thetas at work. Now the common points. It looks like we have a common point at 0, 0. That's the pole. We have a common point here at pi over 6. And at pi over 6, let's see, if you put a pi over 6, that's half. That'll be 1.5. At 1.5, pi over 6. And this one looks like it's also 1.5. Do comma there. And 1.5 comma 5 pi over 6. So these would be, again, the solution. Make note, the solutions are actually the spots where mathematically these two equations are the same. A common point is where the graphs are intersecting one another, but they're not mathematically at the same theta happening. All right. Now, from last lesson, when we talked about polar functions, we went through and had these four formulas right up here and these rules to help us find a point. We're going to use all these four formulas, and we're going to convert from polar equations to rectangular and rectangular to polar. So my four formulas that I'm going to be working with, just to make sure you remember, is that x is equal to r cosine, y is equal to r sine theta, x squared plus y squared equals r squared, and finally that tangent theta equals y over x. Those are our four formulas that we're going to use to convert from one type of equation to another. So if I wanted to express that equation in polar form, how would I do so? As I would exchange. So y is the same thing as r sine. So r sine theta equals 1/2. And x is the same thing as r cosine theta, and I'd square that. Now I'm going to multiply these out. PEMDAS, you got to do the exponent, the parentheses first. There's nothing to do within that parentheses, so now I do the exponent, which means I multiply. So this is r cosine theta times another r cosine theta. From here, what I can see is on both sides of the equation, I could multiply by 2. I'm going to do that to help myself out. And I'm also going to divide both sides by r. Now, r, by rule, is not supposed to be 0. It's supposed to be a positive number. Therefore, I can divide by r without changing the equation because I'm not dividing by 0. So if I multiply by 2, why did I do that? This goes away. And so we have 2 sine theta equals just one r left over. Cosine times a cosine. Now what I will do, I'm trying to isolate the r to get in polar form. You isolate the r. I'm going to divide by this cosine squared. Divide by this cosine squared. And so I'm left with r equals 2 sine theta over a cosine theta times another cosine theta. Now, why do I write it this way? Because according to the quotient identity, a sine divided by a cosine is tangent. That's the quotient identity. That's going to be a tangent. And then dividing by a cosine, according to the reciprocal identities, dividing by a cosine is the same as mathematically multiplying by a secant. And that's a reciprocal identity that I'm telling you. Reciprocal identity. And so I can change this equation to be r equals 2 times the tangent theta times secant theta. And that would be my answer right there. All right, let's reload and try this again. Let's try this rectangular form into polar form. Well, using our four formulas, I'm going to say that I have 4 times r cosine theta squared times r sine theta equals 1. Now, since I just multiplied that out and showed you how that worked, I'm going to do it again. These, of course, can separate like I did over here. So this will be 4, and this will be an r squared times another r. It'll be 4r cubed times a cosine squared, or you could do cosine times cosine, times a sine theta equals 1. Again, I want to isolate this r. So I'm going to divide by is 4 cosine cubed times sine. 4 cosine cubed times a sine. And by the way, the cubed is not the theta, it's the cosine. That's what's actually being cubed. So 4's cancel. Cosine, oh my goodness, that's not a cosine cubed. It's a cosine squared. Let's fix that. And the sine cancels. So what am I left with? R cubed equals 1/4. Now we have two reciprocal identities. Both of these are reciprocal identities. And so it's 1/4. Dividing by a cosine squared is the same thing as multiplying by a secant squared. And then dividing by a sine is the same thing as multiplying by a cosecant. So you could leave it as r cubed, and I'll do it that way. I'm just going to leave it like that. And that would be my equation there. You could do a cube root if you so desire. Okay, I have a couple more here. What about if I just had r equals 4? And I'm going to paste my formulas so we can refer back to those. There they all are. So if I have r equals 4, the easiest formula as I look up there to make it like is r squared. If I want to square, I need to square both sides of the equation. So I can say this is r squared equals 4 squared. If I square both sides of the equation, that's mathematically okay. Well, r squared is the same thing as x squared plus y squared. And 4 squared is simply 16. That is good rectangular form. That's going to be a circle right there, believe it or not. That's a circle. And now let's talk about this last one. Theta equals 2 pi over 3. Well, if I look up there, the best one for this is here, this theta. All I have to do is take a tangent of both sides. That's the same thing as tangent theta equals tangent of 2 pi over 3. Tangent theta is y over x. And if I do a hand trick here, 2 pi over 3, make a note, 2 pi over 3 is in the second quadrant. 2 pi over 3 is over here, which means x will be less than 0, but y will be greater than 0 because x is to the left, y is up. So tangent 2 pi over 3, pi over 3 is my index finger. If I bend my index finger and flip my hand, I get a positive square root of 3 for the y, but I get a negative square root 1 for the x. I can reduce that. So it's y over x equals square root 3 divided by negative 1. And y over x equals, that's just negative square root 3. Then I multiply both sides by x and I'll have my equation. So I have my equation y equals negative square root 3 of x. There's my equation there in rectangular form. 2 more to try to make it a little trickier. So let me again paste my formulas so we can have those to refer back to. So here's our formulas. This one is a little bit trickier. I need it to be r cos. Notice I don't have r cos. So what I'm going to do this time is I'll multiply both sides by r. So I have r squared equals 6r cosine theta. I just multiply both sides by r. Now, why do I do that? What happens with the r squared? That r squared, I can make that x squared plus y squared equals 6. And then the r cosine becomes x. Now, typically this isn't how you would leave it in rectangular form. You would need to complete a square, which is unit 4. What I would do is x squared minus 6x. I'd subtract 6x from both sides. Plus y squared equals 0. And you would complete the square right there. That's beyond the scope of what we're gonna do here. So completing the square, what happens is it's minus 3 squared. And since what happens there is if you multiply that out, I need to show the work. Complete the square. So what I would do is you take your x, actually I'll write it this way, I'll just write in the steps. You have x squared minus 6x plus, you add a blank, plus this y squared equals, since I'm gonna add a blank over here, I'm gonna add a blank over here. Whatever I add on the left, I gotta add on the right. What you do is you take your b and you divide it by 2. So it's b divided by 2. So we have negative 3 divided by, I wrote the answer, sorry. Negative 6 divided by 2, which is equal to negative 3. And then you square that value. You take whatever your b divided by 2 is. So that's what I did there. Now over here, you take your b divided by 2 and you square it. That's what's going to happen right here. So I'm going to square this. And so when I square that, I get a 9. Negative 3 times negative 3 is 9. Now that is, if you did an x method, you'd see that's a perfect square. That is the square x minus 3. Negative 3 times a negative 3 gives you positive 9. Negative 3 and another negative 3 give you negative 6x. So it's x minus 3 squared plus y squared equals 9. There's your equation right there. That is a circle that's shifted to the right 3 units and has a radius of 3. That's what that would be. Circle that would go out, have a maximum at 6, and it's to the right because it's a positive cosine. All right, and the last one here for me. What if we were going to use this one? So there's my answer, and I just grabbed it for you. You can see the red and the blue are kind of overlapping. They're the same graph. Let's try going backwards. So here again, we have a circle. Let's see what our equation would be. Now, what can I do first? Well, I could substitute some values here. X is the same thing as r cosine. So we'll say that this is r cosine theta. You know what? I'm going to distribute this first. I think it'll be easier. If I multiply this out, what here I would get is a x. Think about multiplying it times a cell. Let me just write it out. X minus 3 times x minus 3 plus y minus 2 times y minus 2. And all that's going to equal 13. So when I multiply this out, when I distribute, I have x squared minus a 3x minus another 3x, which is minus 6x, plus 9. There's that perfect square I was just talking about earlier. Plus y squared minus 2y minus another 2y is minus 4y plus 4, and all that would equal 13. Now I'll substitute. We know x squared and y squared together. X squared and y squared together can become r squared. And then negative 6x right here, this negative 6x becomes minus 6r cos theta. Negative 4y is minus 4r sine theta. Plus 9 plus 4 is 13. What I can do with all this is if I subtract this 9, if I subtract this 4, then I need to subtract 9 and subtract 4. All of that would equal 0. Those cancel, and that is subtracted by 13. Those cancel. We're equal to 0. And so to solve this, what I'm going to do is I'm going to add over now. So that's a lot going on. I get it. I'm going to add over a 6r cosine theta and add over a 4r sine theta to both sides. 6r cos theta plus 4r sine theta. And so I'm left with r squared equals 6r cos theta plus 4r sine theta. We're almost done here. I have a GCF on this side. if I GCF'd out, you can notice I have an R that I could pull out of on both sides here. So it's a 6 cosine theta plus 4 sine theta. Now what can I do? I can divide both sides by R, and we'll finally have our solution. That this becomes, this R cancels with one of those two. We have R equals 6 cosine theta plus 4 sine theta. Let's check our work and see if these graphs match. That's what I'm going to do now. I'll come over here to this graph, and I'm going to change my equations. It was x minus 3, and this needs to be y minus 2 quantity squared equals 13. There's that circle I was talking about that was going to be. And then my second equation here, we're getting 6 cosine theta plus 4 sine theta. And I press enter. Perfect match. We did it correctly. So with that, you have your DOL. And that'll be a wrap for the lesson.